negative 2.3, I plugged in the first step of this. I don't know. I probably printed it. Why did they say that? They need words. Okay. Equilibrium. Today, tomorrow, and Thursday, we're just going to learn, actually most of this unit, this first chapter, is just on like the basic math of equilibrium. We will spend an entire month on equilibrium. It's huge. It involves all acids, bases. It involves everything precipitation. Like we have a long way to go with equilibrium. So what is equilibrium? Remember, way long time ago, we talked about that if we had A plus B, I'm drawing an equilibrium arrow on purpose, make C plus D, that A has to collide with B in the right orientation with enough energy to overcome activation energy, collision theory, in order to make C plus D. But then I brought up like, what then would stop C from running into D and then making A and B? Nothing. There would be no reason that C couldn't run back into D with enough energy to overcome activation energy in the right orientation, and it would turn right back into A plus B. That's what equilibrium is. Have you ever done this at like a restaurant where you just like change the air pressure and then it like creates a little suction? Okay, so pretend these are our reactants. Yellow is in, orange is the products. So this is like not brain eyeballs. This is like real eyeballs, but this is how I see it. So if my reactants are turning into products, I have less reactants and I'm making more products. I have less reactants and I'm making more products. They're colliding and they're turning into that, okay? But remember, there's nothing that would stop these guys from running into each other and turning right back into the yellow stuff, right? When this happens at the same rate, that's called equilibrium, okay? So now you have a party trick at the restaurant table. And you can tell your family what equilibrium is, as long as your brother lets you touch his straw, which is not too much. Okay, but now our eyeballs though, like in a real reaction, when this happens, it looks like nothing is happening. Okay, so at first we're like, look it turned purple. I made all this purple stuff. But then eventually, like that all wears off, and then it's like, okay, the reaction's done. It's not actually stopped. It just means that they're turning back and forth at the same time. Okay? So equilibrium is when the rate of the forward reaction, A and B, equals the rate of the reverse reaction. That's a really aggressive C and D. To our eyeballs, it looks like nothing. Because purple's turning back, but at the same time it's turning back to purple. So when we look at it, we're like, okay, nothing's happening. But really, it's just happening at the same rate. Okay? When the music starts, just give a general overview of what equilibrium is and how you probably shouldn't touch other people's straws. Ready to go. Okay, let's draw a graph. I paged a little bit. I'm going to use red and blue. They did, if you're like trying to compare to what this is, they did blue to red, but I don't know why. Red seems that it has to go first to me, red then blue. So I just have to do it that way. Okay, some things about these graphs. The proportions matter, okay? So A is turning into blue to B. So red is disappearing, blue is appearing, okay? But it's happening at a ratio of 1 to 2. So every one red that's lost, I'm gaining 2 blues. So when you draw your lines, you have to draw them in proportion. That's like a point. So at time 0, I have lots of reactants. Nothing has happened yet. At time 0, I have no products. Nothing has happened yet. Like I haven't made anything new. So we played this game last unit where it's like disappearing, 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 harder and harder to find, and then it just kind of evens out. That's called rate. It's like the change in concentration over the change in time. Now we're going to add a second line, our products line. But we have to draw proportionally. So for every 1 red lost, I'm going to gain 2 blues. So I'm like trying to make the slope twice as big. Do you know what I mean? I'm gaining faster. Oh, wow. I'm talking and drawing at the same time. It should be like smooth. Okay. The point where my rate, my change in concentration over change in time, is when we say equilibrium is reached. To our eyeballs, it looks like the reaction is done. Up until this point, we're like, oh, it's over. Like, it stopped making bubbles. But really, they're just turning back and forth into each other at the same rate. We can't tell the difference, okay? So things I need to talk about. I need to talk about proportions of lines. So if this was reversed, like on that poster, I purposely did it backward. Why is the red steeper than the blue? And then just make sure you understand your axes. Ready, set, go.
Sam, I literally got it to apologize. I know what it is.
Okay, page to pages. Okay, I know in the notes they skipped letter C because I think it's hard to distinguish a lowercase from an uppercase. I'm not skipping letter C because we've just been playing ABCD this whole year. I don't want to change it now. Okay, we're going to learn a new K. This K is a capital K. There's 6 different versions of this capital K. Today is first K of all the Ks. It is different from lowercase rate K. Lowercase rate K, you have to solve for, and you have to find units for. Uppercase K, you do not have to do units for. They exist, you just don't have to do them, okay? Uppercase K is equilibrium K. It's equal to our products, the concentration of our products, to the power of the coefficient. Remember, brackets means concentration. So we're taking those molarities over the concentration of our reactants. Coefficients become exponents. That is called Kc, C for concentration. Same game. Same game, but you can play it with pressures too, with ATM. It's called Kp. P for pressure. Pressure is ATM. Like the data you're given is an ATMs. But you're going to play the same game. Equals our products, but instead of brackets, I'm just going to call it pressure of C to the C times pressure of D to the D over our reactants, pressure of A to the A. Any coefficients become exponent. Pressure of B to the B. Just in case you were just like caught up in copying what I'm doing, can you just make sure the person next to you understands where the numbers are coming from? What is A, what is B, what are the exponents? Ready, go. Okay, I don't know why, but the Haber process is the one and only balanced equation like you have to memorize. Okay, so the Haber process is the production of ammonia. Ammonia is NH3. So the balanced equation for the Haber process is taking diatomic nitrogen plus diatomic hydrogen to make ammonia, and then you just like balance it with a 3 and a 2. I don't know, sometimes it's like a writer's research and then they get like a learning objective in there that's really obscure. This is just one of them that for some reason you might have to regurgitate the balanced equation for the Haber process. So this whole unit is like filled with it, and I'm just going to keep saying it over and over and over again to help you remember. But the Haber process, let's practice. Let's practice writing our K equation. I'm going to pretend it's molarities just because brackets are easier than P's to me. So we take our products. So I would take my NH3 over our reactants, and any coefficient becomes an exponent. I don't write ones, but you're not wrong if you do. So like you could write a power of 1 if you wanted to. I just don't. Okay, so Haber process is how they make ammonia. I don't know why you need to know that, but you do. You can cross off this whole thing. They took it off the equation sheet this year, which means you are not going to be asked to do it, which is awesome. One less thing to do. Okay, what does K mean? Let's write our A plus B yield C plus D again. Just so like we're speaking the same language, this is called the right, this is called the left. It's to the arrow. So the right of the arrow, the left of the arrow. The right of the arrow, we call these products. I think you know that, I'm just reminding you. And we call this reactants. When I plug my numbers in for K, and if K is greater than 10, and I don't know, but you have to write greater than 1. Greater than 1 means greater than 10. Like the extra arrow means like an extra decimal place. We say that the equilibrium lies right. Like those are the words. Lies right. Yes. Nope. You have to write greater than 1. I don't know. Write a letter to the dead like I made it up. Okay. What does this look like to our eyeballs? If the equilibrium lies right, and the right are the products, to our eyeballs, look at all this purple stuff I made, or look at all these bubbles I made. It means that our equilibrium is mostly products. We have tons of products and not a lot of reactants. Look at all this new stuff. If K is less than 1, that means 0.1. We say it lies left. The left side is our reactant side. So to our eyeballs, it looks like nothing happened, right? If I have mostly reactants and I'm not making products, nothing has happened. I didn't make anything, nothing has happened. Okay? So when we have a really small K value, we usually say no reactions. Because it's mostly reactants, and reactants is what I started with. So I didn't make anything new. Okay, when the music starts, talk about K being greater than 10, K being less than 0.1, and what our eyeballs see. Ready, go. Thank you. If K equals 1, then the words are it's at equilibrium. So when we do a reaction and it's all over, to our eyeballs, it looks like it's done, and we took the concentrations of everything. K is going to equal 1. Okay? You know how we play Hess's law a lot? Hess's law is where we add the reactions together and we cancel the stuff. We are going to play that with K's as well. So if I have to reverse the reactions, because you know how sometimes you have to like flip-flop them to get them to cancel? If I have to reverse the reaction, I'm going to take 1 over K. Where when I had my enthalpy, I just made it negative. K is a little different. I'm going to take 1 over K. If I had to multiply the reaction by something, so you know how sometimes it's like, okay, times 2 to make everything cancel? You have to take the K to that power. So like K squared if I multiplied everything by 2. Instead of just multiplying the enthalpy by 2 like we used to, K's are going to be different. We're going to take it to the power of 2. And you know how we have to add them together? We're going to actually multiply them. Is there an apostrophe? So instead, we used to just add down. Now we have to multiply down. Let's do some sample problems, though. So can you flip back to sample problems? We're going to start at number 1. I'm just going to have you practice with your beta buddy. Go ahead and do number 1 with your beta buddy. Writing the products over reactants, coefficients become exponents. Pure solids and pure liquids don't have molarities. They don't have pressures, so they don't go in equilibrium. Only aqueuses have molarities. Only gases have pressures, have ATMs. So only aqueuses and only gases go into K. Everything else gets eliminated. Okay, so now do number 4 with your beta buddy. Okay, now do number 5. So for number 5, what you're doing is you're actually going to plug in numbers. Okay, so many words, paying attention to like what goes with what. After a mixture of hydrogen, nitrogen gases, this is the Haber process, is allowed to attain equilibrium. So to our eyeballs, it looks like nothing's happening, but really they're just turning back and forth into each other. Okay? They're always going to give you a temperature because temperature matters for K. We just haven't learned why yet. I have ATM, so that means I'm doing KP. P for pressure. Same game, just instead of brackets. Plug everything in and see if you can get a number. Like push buttons and get a number. Ready? Go.